Hello and welcome. So, if you're getting ready for big exams like GATE or JEE, you already know thermodynamics, it's a total game changer, right? It can be the thing that makes or breaks your score. So, in this explainer, we're going to dive right in and build a super solid foundation, starting from square one. It all really boils down to this one big question. I mean, look around. From a massive power plant to the engine in your car, how do we even begin to analyze all that energy? Well, the answer? It's thermodynamics. That's the science that gives us the playbook, the tools we need to understand and engineer pretty much everything that powers our world. Okay, so before we can jump in and start solving problems, we have to do something really important first. We have to decide how we're going to look at things. It's like choosing the right lens for a camera. And believe me, in thermodynamics, this first step, it changes everything that comes after. So here we've got two different paths we can take, and honestly, this choice is everything. On one hand, you have the microscopic view. We could, try to track every single zipping molecule inside an engine, but wow, that's insanely complicated, right? So for engineering, we do something much smarter. We use the macroscopic approach. We look at the big picture, the stuff we can actually measure, like pressure and temperature. This is the practical way, and it's exactly what you'll need for your exams. And this whole macroscopic idea, it's built on one really clever assumption called the continuum. Now, we all know that the air in a room isn't solid, right? It's a bunch of atoms with empty space. But we kind of pretend it is. We treat it like a smooth, continuous blob. And why do we do this? Well, because it lets us use all the powerful tools of calculus. It makes the math work. It's a simplification, for sure, but it's a super powerful one that works perfectly for the kind of problems engineers solve every day. Okay, great. So we've got our lens. We're looking at things from the macroscopic view. Now what? Well, the next logical step is to point that lens at something. We need to draw a circle around the specific thing we want to study. And this is where we get to three of the most important words you'll ever hear in this subject: system, boundary, and surroundings. Look, the system is simply the thing you're studying. Maybe it's the coffee in your mug. The boundary is the line you draw around it, the inside surface of the mug. And everything else in the universe, that's the surroundings. And I'm not kidding. Getting this right at the start is step one for solving pretty much any thermo problem you'll ever face. All right, so let's put this into practice. You've got two main types of systems. First, a closed system. Imagine a sealed tank of gas. The amount of gas inside is fixed, right? Mass can't get in or out, but energy, like heat, can. Now, the other type is an open system, which we often call a control volume. Think about a jet engine. Air and fuel are constantly flowing in and exhaust is flowing out. See the difference? Mass is crossing the boundary. Both mass and energy can move in and out. Okay, quick pop quiz for you. Think about a sealed pressure cooker. Water's boiling inside, turning to steam. Is that system open or closed? Well, the key word there is sealed. No steam can get out, no water can get in. The total amount of H2O inside is stuck. So even though it's changing phase, it's a perfect example of a closed system. All right, so we've picked our system, we've drawn a boundary around it. Now, how do we actually describe it? Like, what's its condition right now? To do that, we need to talk about its state. And the way we describe a state is by using its properties. A property is just any macroscopic characteristic you can measure. Think of them like the vital signs of a system. Pressure, temperature, volume. These are the numbers that tell us exactly what's going on inside. They're the language of thermodynamics. Now listen up, because this is a classic exam question. You absolutely have to know the difference between intensive and extensive properties. It's actually super simple. Intensive properties do not depend on how much stuff you have. Think temperature or pressure. If I take a bucket of water at 90 degrees and split it into two smaller buckets, the water in each is still at 90 degrees, right? But extensive properties like mass and volume do depend on the size. If I split that bucket, the volume in each new bucket is now half of what it was. So that's the trick. Just imagine cutting the system in half. If the property stays the same, it's intensive. If it gets cut in half, it's extensive. Got it? But there's a little catch. For us to be able to talk about the temperature of a system, it has to be the same everywhere inside, right? That state of balance is what we call thermodynamic equilibrium. It just means everything's settled down. There are no hot spots or cold spots, no high pressure areas. Everything is just calm and uniform. So we've got this whole list of properties.
Pressure, temperature, volume, density, all these things. But here's the million-dollar question. Do we need to know all of them to know what's going on, or is there a shortcut? How many do we really need to pin down the exact state of our system?
And the answer is amazing. It comes from something called the state postulate, and it is a massive time saver. It says that for most simple systems, and that covers almost everything you'll see, like air, water, steam, you only need to know two independent, intensive properties. Just two. If you know the pressure and the temperature, that's it. You've locked in the state. You can figure out every other property from just those two pieces of information. How cool is that?
And that is why diagrams like the PV diagram are so incredibly useful in engineering. They're basically maps. The two axes are your two independent properties. You find your pressure on one axis, your volume on the other, and where they meet, bam. That single point on the graph tells you the complete state of your system. It's a visual way of using the state postulate.
Okay, so far everything has been about a system just sitting there in one state, a snapshot in time. But let's be real, the interesting stuff happens when things change, when an engine fires, when water boils, when a system moves from one state to another. And that change almost always means one thing. Energy is on the move, crossing the boundary.
And when energy crosses that boundary, it does so in one of two ways: heat or work. Heat is pretty intuitive, right? It's energy transfer because something's hotter than something else. Work is, well, it's pretty much all the other ways energy can be transferred, like a piston pushing something. But here is the single most important thing to get right. Heat and work are not properties. A system doesn't have heat. It doesn't have work. These are things that are happening to the system. They are energy in transit. They depend on the path you take from state A to state B, not just the destination.
And when we talk about work, especially for engineering, you'll see a few common types. First, there's boundary work. That's a moving boundary, like a piston in a cylinder being pushed by hot gas. Super important. Then you've got shaft work. That's the work you get out of a rotating shaft, like the one that turns the wheels of a car. And of course, there's electrical work. Just being able to spot which kind of work is happening is a huge part of solving these problems.
So let's just pull back for a second. We figured out how to look at the world, how to define the thing we're studying, how to describe its condition, and how to track energy as it comes and goes. We have all the building blocks. But that leads to the big one, the question that ties it all together. How do we balance the books? How do we account for all this energy? Well, answering that question brings us to one of the most fundamental laws in all of physics, and it's exactly where we're headed next, the first law of thermodynamics.